yesterday, we did some unconstrained. We started with unconstrained. What did we talk about here? Sorry? Right. So if you do exact search, what happens when you do this? Yeah. Yeah. Uh-huh. Yes. At every point, the gradients, but at every step, not every point. See. Okay. If I moved in this direction now, my next movement is going to be in a direction orthogonal to that. But here you have to solve this problem. You have to minimize alpha k exactly to be able to exact line search. Okay. And then, yeah, Newton's method. What is the generalization of Newton's method in Rn? Now, the update rule is xk plus 1, simply xk. Okay. What is the basic idea behind the Newton's method? Yes, this is a bunch of second derivatives. Yeah, that is by the minus sign. But what is this doing here? Right. You can say this is alpha k, fine. But why this particular choice? This is some weird choice, no? Inverse of the Hessian. Right. So this kind of accounts for, because the problem in choosing alpha k is alpha k depends on the curvature, local curvature at point xk, accounts for the curvature of f of x at xk. Okay. So it works well. And in fact, if f of x is quadratic, it works perfectly. You only need one, no matter where you start from, you only need one step to reach the global minimum. If you're dealing with a quadratic function, um, right? But when does it fail? Right. The condition here is h of xk should be can be greater than or equal to 0. If it's 0, then there is a condition on your gradient as well for you to be all right. Otherwise, you can run into problem if it's equal to 0. It fails when this condition is not satisfied. What does it mean geometrically when your Hessian matrix is not positive semi-definite? Sorry. Yes. So the resulting vector will get rotated, or the resulting vector will have a component along the direction of the gradient. That means there is essentially a change of sign here. That means you're moving away. You're essentially increasing the function. So that can be a problem. Okay. And what is one way to fix this? Right. You ensure this never becomes. You ensure that this is always positive definite, at least positive semi-definite by what do you add? And on the I inverse. Yeah. Okay. And lambda is number greater than what? Well, it's not sufficient if it's just greater than 0 if there are some negative eigenvalues for your h of xk. So what should this be greater than? let's say the eigenvalues of this are lambda 1, lambda 2, lambda n. Which lambda? There are n lambdas, no? There are n eigenvalues. What is the condition to ensure that this is always positive definite? So you're saying lambda should be greater than the highest? Is this the condition? Is the highest the requirement? See, that's correct. If you're greater than the highest, you're ensured. Okay. Um, well, it depends. Um, if all your lambda i's are negative, right, then you of course have to be greater than the highest value. Okay. Uh, but um, another way to say this is you have to be, it's of course it's greater than zero. This has to be greater than, let me write it like this, 0, lambda is greater than 0, and lambda has to be, yeah, that's fine. Lambda is greater than the absolute value of, that should be okay. If it's, so if you set lambda to be a positive value greater than uh, the absolute value of the lowest possible eigenvalue, then you're okay. If the lowest value is -5, then you set this to be a value greater than 5, then everything else is okay. If there is a -4, 5, well, let's say I set it to 5.5, this will be positive, this will be positive, everything is okay. So if you set it to a value like this, then you're all right. See, of course, you don't have to worry about this. Let's say you know the eigenvalue, absolute value of the eigenvalues cannot be lower than 100. So you say, I'm going to set this to 5, 10 power 5, because there is no way, I mean, the chances that an eigenvalue will be, I'll have an eigenvalue lower than -10 power 5 is very small. So I say this. But what is the problem if I set it like this? No, direction won't change. This is positive definite. That means you'll never rotate this by more than 90 degrees or plus or minus 90 degrees. You understand the issue? You have to set lambda such that this is always positive definite. That means if you set lambda to be a very large number, then there is no problem. Like this will always be positive definite. Why not do that? Why worry about choosing an appropriate lambda? What will be alpha k? Will be small, because if these are your eigenvalues, uh, well, if lambda is very small, the eigenvalues of this matrix are very close to 10 power 5. You're taking the inverse of that. The inverse of, if you have a positive definite matrix with eigenvalues lambda 1 to lambda n, what are the eigenvalues corresponding to H inverse? Well, it will be lambda 1 inverse and the n inverse. So if you set a very large lambda here, then this uh, the entries in this matrix will be very small. So that's equivalent to saying your alpha k is close, means your progress would become very small. So you cannot freely choose a very large lambda here, because this will become a small, so this term will become very small. Okay. So you have, it's necessary that you choose lambda appropriately. Okay. Okay. After this, that was the end of unconstrained, and then we switch to constraint. What did we talk about? Right. So we said now the optimization problem is the full problem. Okay. That means our search is now not now all over Rn, but it's in a restricted set, omega. Okay. And omega is simply what? Set of x uh, belonging to Rn. that satisfy this. Okay. So you are only searching over this omega. Okay. If that is the case, now we need to ask, okay, in the unconstrained case, that we had a set of conditions for knowing if I'm here, and let's say these are the contours for my function. This is my f of x, and this is the region where both of these are satisfied. G of x is less than 0. H of x is exactly equal to 0 in this set. If in the unconstrained case, if I'm a particular point, there is a condition for me to know whether or not that point is a local minimum. What is the corresponding condition here? For the case where you can only search within a particular set, and this is called the feasible set. Okay, if this is a minimum, then the gradient of f at x star, what is the direct, it's not any direction, but it's a, what is the feasible direction? No, not really. Okay, more or less. Feasible directions are, if you're at any point, well, feasible directions are essentially direct unit vectors associated with any point in this set. Feasible directions are directions in which if you can move by however a tiny amount you want, and you will still stay within the set. Okay. For example, if I'm here, I can move in any direction. Okay. By a non-zero amount, and I'll still stay within the set. Of course, if I make a large step in this direction, of course I come out. But I can always take a smaller step and stay within the set. Okay. If I'm an interior point, right, then all possible directions are feasible directions. But if I'm here, right, I I of course cannot move in this direction, or in fact any of these directions. All I can do is move. So if this is the tangent line to this point, I can move uh, in in all of these directions and still stay within the set. So the set of all these directions is are the feasible directions at any given point. The set will change depending on where you are. Okay, but this is a more generalized condition. If you have, if the inner product of your gradient at a particular point with all possible feasible directions is greater than or equal to 0, then this can be a minimizer. Okay, if it's greater than 0, this definitely is a minimum, local minimum. Okay, if it's equal to 0, then that's not enough. It might not be. It might not be a minimum. It can be a maximum or an well, maximum or a minimum. Yes. Okay. Right. So that's the first order condition. So if your delta f of, well, okay, uh, this translates to what? If you're this at the boundary, this is, I mean, in fact, this is okay for both the boundary points and the interior points. But if you're in, and if x star is an interior point, what does this condition become? Right. So if you are dealing with an interior point, then this is simply equal to 0. That's the condition. Okay. Okay. Now, if del of x star is equal to 0, okay, then how do we find out whether it's a minimum if this point x star is a minimum? The second order condition. What is the condition? Yeah. What is the condition? If you have, well, you need the Hessian matrix. Okay. Ah. Okay. Okay. Is that the condition that it should be? Well, if it's this, then you have a strict minimum. It can be positive semi-definite, and you could still have a minimum. It's just that if it's 0, you don't know. You have to do further analysis to find out. But is that the condition? What is B? What direction? It's again the set of all feasible directions at x stars, right? That means the matrix has to be positive definite with respect to the feasible directions, then you're fine. Okay. That means in the feasible directions, it has a positive curvature. Okay. I mean, it looks like a ball. It does not look like an inverted ball. Then this is okay. Okay. And in fact, if this is satisfied, then it's a strict minimum. Okay. All right. This is where we stopped, and we did a couple of examples. We did a yeah, yeah. Hmm. Hmm. Uh-huh. When we are doing this condition is up, and if x tends to 0, then why did we check why did we check what? This condition. Tell me one. Why did not we stick with all? This one? Ah, here. You could have done this as well. That's fine. This is the most general case. This your mean? Sure, this is easier. I agree with you. Yes, if this since this is not satisfied, um uh, there is no minimum within the feasible set 0 to 1. Yeah. All right. We will do a two-dimensional example again to get this ingrained in our mind. So let's say we are talking about function f of x, this x1 square, this x2 square, and our h of x. Well, let's say our set is defined like this. If a set of points x or x1, x2, such that x1 is greater than or equal to 1, x2 is greater than or equal to 1. That's our set. Okay. That means the corresponding picture looks like this. So these are our, right? This is our f of x. Where is our feasible set? Where is the feasible set? Well, this is a feasible set. Geometrically, where is it? This is x1. Hey, this is f of x. What I've drawn here is essentially this is ball, right? This is f of x, the different contours of f of x. Omega is my feasible set. It's a set of all points such that f x1 is greater than or equal to 1, x2 is greater than or equal to 1. Where would that be? Hey, hold on. Why will it be circle of radius 1? Is this the definition of a circle? Hey, hold on. This has not, okay. This is this is done. This is f of x, right? This is this ball. Uh, this has nothing to do with omega. Remember, omega is defined only by g and h. Omega has nothing to do with f. Okay. See, look at the way omega was defined there. Omega is set of all x's that satisfy this condition. Okay. Or is it really the first quadrant? You're right. It's in the first quadrant, but it's not the first quadrant. Where is it? Yeah. Okay. But what is the shape of that set? See, another way I could have written this in the standard form is I could have said I have a g of x less than or equal to 0. That's equivalent to saying x1 minus 1, x2 minus 1, minus of this is less than or equal to 0. This is my g of x. This is g1 of x. This is g2 of x. What does it look like? Well, it's just this, right? All of this. So these are all points. If I choose any point, well, these are the set of points where x2 is 1 and x1 is any value greater than 1. These are all the points where x1 is 1 and x2 is all values given. So this is our omega. Where do you think the minimum is? What is your guess? Well, it has to be here, right? Because the ball is going up like this, and this point is essentially touching the ball. Well, this point corresponds to the every other point as you move away, the the height of the ball increases from this surface. Okay, all right. Now, how do we show that? Yeah, you can. If you so okay, now your hypothesis is that this is a minimum point. Let's say this is your x star. Okay, how would you verify that? Well, you need to verify this condition to see if it's satisfied. Just for completion, I will write it like this: g1 x equals minus x1 plus 0. And if you simply apply it here, and this essentially gives you this set of all points that satisfy this gives you that. And now we are interested in finding out whether this point is actually a minimum. Well, we need two things to find out if it's a minimum. We need the gradient, and we need the set of feasible directions. What is the gradient? Let's start with that. What is gradient? What is it? So it's one, it's two, okay. And what is x star? The point that we are considering. This is 1 comma 1. That means the gradient at there is all right. So that we've got one piece of the condition that we need to test. What about D? What are all the feasible directions there? Well, D is really a set of vectors, right? Tell me what, well, you don't have to tell me the algebraic expression. At least geometrically, what are all the possible directions that you can move? What are all the feasible directions at this point? Okay. So if you say it this way, I don't know which way. Can you describe? Uh, you can describe moving towards away from the origin only in the first quadrant. Is that a good description? Well, or arrows that have a positive component along the x1 axis and a positive component along the x2 axis. Is that okay? Okay, all right. That means the the set of feasible directions are d1 and d2 such that d1 is greater than or greater than 0. Let's say we're only zero vector is not a feasible direction. Okay, we are only talking about vectors with, let's say, unit length, right? Is that okay? Okay, all right. Now, how do we verify? Now, you have to simply apply that condition. That means we take, let's say, D is any feasible direction, that is D1, D2. And since this is a direction from this set, both of these are positive numbers. Or in fact, I'm sorry, it can also be 0. Okay? That's because here I can move along this direction and still stay in the set. I can move along this direction and still stay in the set. So that is the complete definition. We could add an additional condition saying the that means both of them cannot be zero. Both of them cannot be zero. Okay? So this is from here, and we want to take the inner product of this with f of this. This will be 2 f2 b1 plus b2. Is this greater than or equal to 0? Yes. These are two positive numbers multiplied by a positive number. This is in fact greater than 0. And we're done. This is greater than 0. That means that point is a minimum. Okay. You can check the interior points and maybe points along any arbitrary point along this boundary. I'll leave it as an exercise for you to do. Let's say we are talking about the same problem, but I change the definition slightly and I say this is uh, x1, x2. Now, how is that different? Well, now you're saying, well, I'm this problem, all this is my feasible set. Okay. Where do you think is the minimum? Well, it's likely to be here. Can you verify if it's in fact a minimum? What are the set of feasible directions in this case? Is it the same as here? It is, right? You can all the feasible directions are directions where you have a positive component, you have a non-negative component along x1 and x2. Tell me what you find for this. All right, you get 0. That means we don't know. Okay. That means now you'll have to apply the second order condition. What is the second order condition? Well, what is Hessian for this? What is the Hessian matrix? Yes, compute it. Well, taking the gradient of this, what will that be? 2, 0, 2 is it? All right, that's correct. Okay. Well, is this positive definite? You don't have to compute now. Is this positive definite? If it's positive definite, then you don't have to compute this, right? The the problem comes if this is not, this is indefinite, right? But it might still be positive definite in these directions. In that case, you're okay, right? But if this is positive definite, this is for sure positive definite for these arbitrary directions or for these restricted directions. So this is okay. So this is in fact a minimum. In fact, it's greater than 0. That means it's a strict minimum there. Okay. All right. I hope that clarifies me. I will leave it as an exercise for you to maybe try this. Okay? But you can do that yourself. We won't do that in class. Okay? So I hope that kind of gives you some idea about, or at least makes you feel comfortable with the new conditions that we have for to test whether a point is a minimum when you have restrictions on the set over which you can search. So now we will now entirely focus on for the rest of this for the next section at least on only equality constraints. Okay? That means we are only going to be talking about problems like this for now. Okay. And again, as I said, since we are only talking about continuous optimization, we will in general assume that both of these are continuous and differentiable at least twice for now. Okay. Right. Now, if let's focus on this. Right. Okay. This is in general a set of we said this is of size. There are q equality constraints here. With that means we have q functions like this. And each of these functions maps from Rn to R. Okay. So that means this set of equality constraints now restrict the set of values of x that you can search over. Okay, let's look at some examples and then maybe that's clear what is happening. Let's say we're talking about a problem, some f of x, and let's say we only have one, and let's say we're only talking about R2 for now. H of x equals okay, x1 plus x2 equals 0. Okay, that's my condition. Okay, and since we are talking about R2, then where is my feasible set in this space, assuming this is R2? Well, the feasible set is the set of points that satisfy this. What are the set of points that satisfy this? Okay, so where do those points lie? So if I were to draw my omega here, how would I draw it? Well, yeah, it's simply this line. Okay, if I had said this is not like this is -1 equals 0. Well, it'll be shifted. It'll be shifted here. Or in fact, if I had said something like this, well, the condition is some C transpose X minus D equals 0, where C is from R2 and D is a real number. Then what? Well, sorry? Yes, it will be some arbitrary straight line. It will be some straight line here. That's your C transpose X minus D equals 0. Okay. So that means whenever you see a constraint like this, you immediately know what you're dealing with. At least in R2, well, in R2 this is a line. What if X was in R3? Well, I'll remove this for now. What would this correspond to? It means, so in general here, when I write it like this, C is from Rn, D is R. It's a plane. In R3, this essentially describes a plane. Uh, if D is 0, it would be a plane that passes through the origin. That means it's a subspace. If D is not 0, it's not a subspace. It's what is called an affine space. Okay. In higher dimensions, this is essentially a hyperplane in higher dimensions. Okay. What about this? Let's say we are again starting with R2. Well, that's simple. Sorry, it's a circle. So if you had equality constraint like this, that means your search can only happen along the circle. You only search along these points. If for this case, you only search along this. Now, depending on what, I mean, you could have other forms, you could have an ellipse, parabola, whatever you want, right? And what I'm trying to get at is in each of these cases, each of these constraints, H1, H2, H3, defines an one-dimensional manifold. Okay, manifold is simply a continuous surface in some higher dimension. Okay, each of these, each of these defines a one-dimensional manifold, right? The more you I mean, and each one of those, for example, if you have one, then you're searching over a one-dimensional manifold. If I'm sorry, no, hold up, no, I'm wrong. No, each one of these defines a manifold. Okay, okay, of some dimension. Okay, the dimension of each one of these describes a manifold of dimension n minus 1. Okay, if you look at this, if you look at R2, H1 of x defined a line which is a one-dimensional manifold. Uh, that is basically 2 minus 1. Okay, if it was an R3, this equation described a plane. That's a two-dimensional manifold. 3 minus 1, two-dimensional manifold. If instead of being in R2, if I had written it like this, if in 3 dimensions, this is a sphere of radius 1. Okay? Sphere is again two-dimensional. That means this one now describes, in 3 dimensions, it describes a n minus 1 dimensional manifold. Okay? The moment you add another one, the set of feasible points, each one of these describes n minus 1 manifold, but the set of points that you can search over is the intersection of both of these. Okay, set of points that satisfy both of them. The intersection of two n minus 1 dimensional manifolds would be n minus 2 dimensional manifold. Okay, that means if you have q equations, okay, well, if it's not clear, for example, let's say we were talking about R2. Okay, I'll remove this. Let's say we were dealing with the problem in R2. I had one equation like this, C1 D1 equals 0. And let's say I had another equation like this. And there will be some other line like this. Where is the set of feasible? What are the set of feasible points in this case? When if you have two H and well, it's just this point. That's a zero-dimensional manifold. There were two of them. Each one defined a one-dimensional manifold. The intersection of them gives you an n minus 2-dimensional manifold. And n is 2, that means you get a point. Okay. So if you have, so essentially, if you put all of these together, or if you look at this vector function, right, this is describing n minus q manifold in Rn. Okay. So your search is essentially on this n minus q dimensional surface in an n dimension, that is inside an n dimensional space. Is that clear? Okay. That's the first thing to remember, that the equality constraints effectively describe a n minus q dimensional manifold. Okay. Now, it turns out that the local property, so you have this high dimensional surface, the behavior of h of x and its relation to f of x at any point in the feasible set essentially determines whether or not a point is a minimum, okay, that we are searching for. Okay, and to understand the local property of any function of this form, we define two ideas. Okay, first one is called I mean, these are fairly intuitive ideas, except that they are now generalized to a higher dimensional space. Okay. Tangent space and normal space. Okay. Now, let's say well, I'll simply define this to start with. Okay. You have h of x. Okay. Even before that, okay, if you take the gradient of this, what would you get? You remember if you had a vector of functions mapping from Rn to R, and you take the gradient of that, right? So this would simply be the gradient h1 of x, h2 of x. Okay, and I'll put a transpose here. Let's assume we're taking the gradient with respect to the appropriate vector, row vector or column vector to get this. Okay, what will this be at some point x? What will each one of these be? What will be the size of this gradient of h1 of x? Well, it'll be n cross 1 vector, right? I'm taking the transpose, so it's 1 cross n. That means, and I have q of those. That means what I get if I take the gradient of my h of x, my equality constraint, is the q cross n matrix. Okay, that's the first thing. So this is which essentially tells you something about how the function changes at this point x. Okay, okay, and both of these spaces are related to how the function changes at this point x. Okay, okay, the tangent space is very simple. Okay, this is a matrix. Okay, you remember the four subspaces? They come back to haunt you now. Okay. Okay. The tangent space at a point x is simply, let's see if you remember. Okay. Is what is that? It's a null space. What is null space? Okay, okay. Null space way is, let's say for now we'll talk about q cross n. What is this? No, it's no. What do you mean? It's a set, right? You have to give me the definition for the set. In what? Ah, yes. Well, they don't map A to 0. A maps those vectors to 0. Okay, maybe you're right. Set of vectors that map to 0 when you apply A. Is that what you meant? Yeah, okay. All right. So it's a set of vectors x from where? Well, there are two spaces, RQ and Rn. Well, if you say one and I give you a bad expression, you know it's the other way around. Okay. Rn. Okay. Well, what is the input space here? What is the output space? Okay, all right. The null space is always from the input space, so it's Rn such that Ax equals 0. Okay. See, this essentially means that if you move in this direction, the effect of applying A is 0. Nothing changes. Okay. If if I have some AY equals B and I add X to Y, I'll still get B. That means if I'm, well, you can think of Y plus X as me staying at X and then moving along, staying at Y. I'm at Y, and adding X simply means I'm moving along X. I move from Y to Y plus X. That does not change anything. That does not change the output that I get. Okay. Okay. And that maybe makes sense here. That the tangent space is the null space of this matrix. That's because if you say you're moving along the tangent space of this function h of x at a particular point, well, not here, here, moving along the tangent space would not change the value of the function. Okay, that's essentially a higher dimensional generalization of the idea of a tangent line to a curve in one dimension. Okay, sorry, I have a curve like this. The tangent to this, well, this is a tangent to this, right? That means if I'm here and if I move along the tangent, the function that, depending on how my function curves, if I if I make very tiny movements along the direction of my changing tangent, my function would not change that much. Okay? Or no, I should not say that. My function behaves as if it is simply a line. Okay. Okay. The higher dimensional generalization of that is if I have, let's say sphere in 3D, and let's say I'm at this point, the tangent space would simply be the plane at that point, which makes contact only at that point with the plane, or with the sphere. It's like this, and this one, this plane touches this two-dimensional manifold, the sphere, just at that point. Okay, that's that's the tangent space. The normal space is simply this. You can tell me what this means. What is that? What is it? Oh, you're correct. That's the row space of what? So this is essentially the row space of h of x. And we know the row space is an orthogonal complement of the null space. So that's essentially your normal space is the orthogonal complement of the tangent space. Okay. Okay. That is equivalent to saying if this is the row, I'm sorry, row space. Okay. Or another way of saying this is the the normal space is simply set of all vectors, okay, that are a linear combination of so it's like this. If I set y1 times gradient of h1 of x plus y2 into the gradient of h2 of x, yq gradient of hq of x, okay, such that y1, y2, yq are all real numbers. So it's essentially the linear combination of the gradients of each of these functions, each of these equality constraints. Okay. See, maybe that's too abstract for now. We'll do a couple of examples and hopefully all of this will become clear. Okay. A compact way of writing this, this is essentially the row space of the gradient matrix here. Okay. And here, if we talk about this example from before, you have the sphere. I don't know if you can see this, but anyway, let's say you're at this point. The tangent space is this plane. Okay. The row, what would be the row space? Where would be the row space? Well, it'll simply be the vector that comes out of the sphere and the plane, and this is orthogonal to the tangent space. This is your tangent space, and this is your normal space at this point x bar on the sphere. Okay. Okay. I'll show an example first on the through an animation, and then we will do some examples by hand, and maybe that will clarify things. Okay. Right. Okay. Forget about the contours. We are not worried about f of x. We're only focused on h of x. H of x here is simply, there is only one constraint. H1 of x equals um, uh, x2 minus x1 square equals 0. That's the parabola. The black curve that you see. Okay. Let's say this is some point on my h of x where I'm sitting, and the red line that you see, that is your, well, that's not really the tangent space, but it's parallel to the tangent space. Okay. And this blue uh, line that you see, that's orthogonal, that is your normal space, or a space parallel to the normal space. Okay. See, you remember both the null space and the row spaces are subspaces of Rn. That means they have to pass through the origin. Okay. The way I've drawn them there, they don't really pass through the origin. Okay. So they're shifted, and they're essentially shifted to the point x. Okay. So you take the tangent space. This is the space that passes through the origin. You simply add this point x, and you simply take this and you add this point. And people will usually call this the tangent plane at the point x, and this is the normal plane at the point x. That's what so the red and blue lines there are the tangent and normal planes at the point black dot that I've shown here on this curve h of x. Now, if I move this, at each point, the tangent plane and the normal plane are of course different, okay, because it's a curved surface. If it was a flat surface, right, then of course the normal plane and the tangent plane will always be the same. Okay? So that's if you have a parabola, if you have no, if you have a circle. Let's say my h of x is x1 square plus x2 square equals 1. Okay. Then you can simply move along the circle, and you see the red and blue lines essentially change because the normal plane and the tangent plane are different at each point on your circle. I don't think I have any. I have this. Yeah. For now, that's all I wanted to say. Okay. Let's do a couple of examples, and maybe that makes you feel a bit more comfortable. Yeah. Okay. Let's say our h of x, we only have one constraint. Let's say we're dealing with R2. How do we find the normal space and the tangent space here for some x at some point x? Let's assume x, this point x satisfies h1 of x. Well, the first thing we do is we find the gradient of h of x. Okay. What is the gradient of h1 of x? Well, remember, we've decided to follow the convention that we will represent the gradient of each of these individual functions as a row, not a column like we've done before. So what will be? So the gradient of this should be a 1 cross n or 1 cross 2 matrix because n is 2 here. So what will we have here? So this will be this one. So fine. If that is the case, um, how do we find out? Well, this is probably easier. Uh, the normal space. What is the normal space here? Well, the normal space is the linear combination of all rows. There is only one row. That means linear combination of all possible rows. What would that be? That means it's a set of vectors which look like this times x1. That's all. Well, these have to be rated like this. Alpha times. Is that okay? I've essentially taken the 2 out. I've incorporated that into my alpha. What about the tangent space? Well, we know the relationship of the tangent space to the normal space. What is it? It's such an orthogonal complement. That means every vector here has to be orthogonal to this. So what do you think would be an expression for this? Sorry? Exactly. So what will those be? What about this? If I use some scalar and I use minus x2 and x1, is that okay? If I take the inner product between these two, the first term will give me minus x1, x2. Second will give me x1, x2. So it'll work out to be 0. So for h1 of x, which is a circle, okay, the radius of the circle does not matter. The normal space is a set of vectors like this. The tangent space is a set of vectors like this. Let's see if that is correct. This is your h of x. Okay. Let's say we are at this point. What would be? How would you draw the normal plane here at this point? What is? Or let me ask you this: what is the direction of the normal space here? Well, towards the origin, is it? Here, the normal space is essentially depends on the gradient of the function. The gradient always points in the direction in which the function increases the most, and the gradient is always perpendicular to a contour. This is a contour. H of x equals, well, uh, x transpose x equals 1. Okay, so which direction is the contour? Sorry, which direction is the normal? Where is the normal space? No, normal space. Let's start with the normal space. The gradient points in this direction, right? This is h. Okay, that means my normal space is a linear combination of all vectors pointing in the x direction. That means it's this. Right? This is my normal space. In fact, that is also my normal plane because its subspace passes through this point, or the set of points include the point that you're interested. What about the tangent space now? So that's essentially this. This is the tangent plane. So this will be your normal plane at this x, and this will be your tangent plane. Now let's see if these agree. Okay. What is your point? What is this point? Value of x at this point? It's 1, 0. Okay. If you plug that in here, you get alpha 0 as your normal space, and your that's correct, right? This is essentially a beta search. The normal space is essentially the x1 axis. The tangent space is different. That's correct. Okay. What about this point where x1 equals x2? Where is the normal plane now? Well, same thing. The gradient is pointing in this direction outward. That means my normal plane has to be like this. And the tangent plane essentially this. And you can verify that here. What is so this will be 1 1 alpha alpha, and this will be alpha minus alpha. Okay, all right. do an example in R3 and maybe that helps you visualize things more clearly. Let's say we are talking about x from R3 and we have two constraints. Or let's say, okay. And then we have another constraint H2, which is essentially something like this: x C transpose x plus D equals 0. Let's see this. Okay. And all of this is a fancy way of saying essentially H2 is this x1 minus 1 equals 0. So D is minus 1. What is this? What is the dimension of the manifold now over which we are searching? Is it two-dimensional? Well, if you have q constraints, what is the dimension of the manifold? N minus q. There are two constraints. Well, each one of these describes a two-dimensional manifold. There are two constraints. That means, what is that one-dimensional manifold here? Hold on. It's one dimension, so it is a line, but a curved line. What is the one-dimensional manifold here? Can you visualize? I'll start with this. What is the one-dimensional manifold? What is the manifold here? It's a sphere of radius 2. Sorry, what is the plane? The second one. Second one is a plane. Okay, where is that plane? Okay, let's assume this is x1, this is x2, and this is x3. Our sphere is sitting here of radius 2. Well, let's say the origin is here. Sphere is sitting here, x1, x2, x3. The sphere is sitting here. If you only had this constraint, then you're essentially moving along this sphere and finding out where is my f of x lowest. But we have an additional constraint, which is where is this plane? Yes, it's the x2, x3 plane, but not at the origin, but shifted by 1 along x1, right? That means it's the intersection of the sphere of radius 2 and this plane here. What do you get when you intersect a sphere with a plane? Circle. Where is that circle located? So where is that manifold? What are these two constraints together defining now? They're defining a circle. Yes, it's a circle. Well, all you have to do was sorry. So you have a sphere. It's not a solid sphere. It's a hollow sphere. It's a shell. Okay, and then you have a plane that cuts through it. Yeah. So if this is your x1 axis, it's a circle around the x1 axis, but located at x1 equals 1. Okay, that's the space. Is that clear? Okay, so that's the manifold that these two are describing. Okay, now tell me, how will we find out the general expression for the normal space and the tangent space? You will never do any of these by hand. Okay, let's be clear. You'll never solve problems like this. The reason I'm going into this is this maybe helps you understand and visualize things a little better and connect your visualization to the algebra. Okay, that's the reason I'm doing this. Okay, all right. Well, for all of this, the first thing to do is the gradient. Okay, let's do that. What is the gradient? Well, we have space here. What is the gradient matrix? Yeah, tell me what that is. Okay. So this is x1, x2, x3. What about the second one? X1, is it? The gradient. 1. Yeah, that's all. Okay. That is at any point on this circle now, that describes my gradient. Okay. Right. Now we will find out what is the normal space and the how do we find the normal space? Yeah, tell me what that is. Okay. So it will be a set of vectors like this. Alpha 1. Yeah, don't confuse this with the step size. This is just some constant. 3. What I'm going to do is I'm going to remove the 2 and let's say that's now in alpha. That means here, this is essentially x. Okay? The value of the vector, that point, plus, is it okay? Okay. What about, tell me what this will be. Well, you have to find the null space of that. That's all. How do you find the null space of that? Sure. So remember, if you have a vector y, the inner product with the first one has to be 0. The inner product with the second one has to be 0. Okay. That means you have, I'll remove the 2, x1, x2, x3, 1, 0, 0. Let's say we are talking about a vector y1, y2, y3. This has to be equal to, sorry, what am I doing? Okay. The first equation is y1x x1 y1 plus x2 y2 plus x3 y3 equals 0. Well, this does not say much. But the second equation is very simple. There, we know at least one of them. Okay, so we don't have to worry about this. Now, what can you say about this? What will this vector look like? Well, the first one has to be 1. Let's say this is eta. This we know. What about the other two? No, it cannot be any vector. If these two are 1, if I put 1 here, 1, 1 here, then I get 2. I don't get 0. Yeah, I think you have it. What is it? Minus what? It'll be minus x3 and x2. Because if I put x2 as minus x3, then I get minus x2, x3. And if I put y3 as x2, then these will cancel out. Okay, hold on. Is this 1? This is 0. Sorry. Okay. Now let's see if that makes sense. Okay. The tangent space contains all the possible tangents to your manifold at any given point. Now your circle is sitting here. Well, this is where we said the circle was, right? This is the x-axis. The circle was here. Where are all the tangents? If you're at any point on the circle, what direction are the tangents pointing at any point on the circle? You sure I mean? X1, this is the x2, x3 plane. The circle essentially is, the plane of the circle is parallel to the x2, x3 plane, but it's located at x1 equals 1. If you traverse that circle, you can compute the tangent at any point. I mean, if you go around, the tangent essentially goes around like this. What can you say about the direction in which the tangent is pointing? Well, one thing I can say for sure, it has no component along x1. right? Because it's in the plane x2, x3. Well, that's 0. Okay, so maybe this is okay. Okay, and in fact, in the previous example, if you look at the tangent space, right, of the circle, it was you flipped x1 and x2, and you changed the sign for one of them. You've essentially done that here. You flipped x2 and x3, and you've changed the sign. So yeah, so you can see it, because wherever, for example, here, if this is your normal space, the tangent space is like this. You can similarly, if this is your tangent space, you'll essentially do the same thing. So maybe this is okay. Okay, and you can verify this. For example, in this example, if I say my point is, let's say the point on the circle that I'm located at is x1 equals 1, which is always 1, x2 is 1, and x3 is 0. Oh, yeah, I got it. We'll finish after this. Okay, on the circle, if I'm at the the location of my point is x1 is 1, x2 is 1, x3 is 0. Where is the tangent vector? Without looking at this, which point, in which direction is the tangent vector pointing? Oh, sorry, let me write it down. Okay, the point you're at is 1, 1, 0. Yeah, it's pointing along. For example, I'm here. It has to be pointing along this direction. What about the normal plane or the normal plane? What is the normal plane now? Yes, it's essentially the x1, x2 plane. Okay. Now, if I'm at some other point, the tangent is pointing like this, and the plane is like this. If I'm here, the plane is like this. Okay, that's the idea. That's for this example. Now you can assume that you can visualize in higher dimensions. Okay. All right. Okay, we'll stop here, and then next week we will complete this, and then uh, talk about, and then look at the inequality constraints as well. Okay, so please make sure you go and revise this, because the conditions for a minimum will depend on essentially the normal space and the tangent space, and its relation to how the function f of x itself changes at any point. Okay, all right. Thank you. Oh yes, yeah.